I'm not very good at this, but maybe with a little practice, I could tell myself to relax it. Will be better next time I try. And even if I still can't do it, yeah, you know that I'm gonna stick to it. Yes, it's all about going through it, and I'm gonna tell you why.
Whoopsie! Whoopsies, I made a mistake and it's okay!
It's okay! Whoopsies are what it takes to get better and better every day. Whoopsies, I made a mistake and it's okay.
It's okay!
Whoopsies, help me look, see, I'm better at this today. Woo! Whoopsies, 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 whoopsies.
I'm a little embarrassed when I look at my drawing compared to this. I'm just not getting anywhere with this. It makes me wanna hide. Aw, don't be embarrassed. Don't hide.
You should have seen mine the first time I tried. It took a lot of whoopsies to look this way.
No one's perfect on their first day. Whoopsie.
Whoopsies, I made a mistake and it's okay!
It's okay! Whoopsies are what it takes to get better and better every day. Whoopsies, 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 whoopsies.
Well, what about this? I want to jump rope, but nope, I just can't do it.
Well, not yet. Come on and practice with me. You'll see there's nothing to it.
Whoa! Whoopsie.
Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Yeah!
Whoopsie! Wait, was it yeah or woo?
I think it was woo.
Okay, say woo with us.
Woo!
There!
Alright, hey guys, this is Taylor from Rootkit. We're here starting day 9. We've got some cool topics to cover today, like multi-threading and multiprocessing. But first, let's start talking about why we're doing this and who we are over at Rootkit. So we get started today. In the description, we have a link to our website. If we go to that, you'll see here that we have a page called 100 Days of Rootkit. If we come here, there's a little blurb here about what we're doing, why we're doing it for 100 days, our timeline that we're doing it for. On the right hand side is a frequently asked questions. So we have things like our Streamlabs charity, which we can get through by clicking over here. This brings us to our Streamlabs charity goal, where we can see that we have $136 out of our goal of $25,000 we want to reach. And at $10,000, we force Elijah to shave his whole head. And then at $6,000, we teach for 24 hours straight until we go delirious. And at $20,000, we shave that beautiful beard right off Elijah. We also have some other ways that you guys can donate to us, such as our PayPal or our Patreon, where we post our companion guides and a bunch of other content. And depending on your tier, you can get a bunch of merch or stickers or other cool perks like being in a Discord, getting a private role in a cool channel that we get priority responses for. We also have our GitHub, where we post all of our certifications and the requirements and resources to help learn for free publicly to everybody. Alright. Oh, I also want to show you guys, we are doing a giveaway. So if you come under the giveaway part and you go to our blog, you can see week 2 giveaway has started as of yesterday. And you come in here, you can do a bunch of different tasks. And by doing these tasks, you get entries to enter the giveaway. The winner of the giveaway gets a bunch of different merch and then some mystery items. Alright. So yesterday we went over digital logic. And we learned some certain things like what a CPU is, the different architectures of a CPU, such as RISC and CISC. And I want to go a little bit more into depth to that as a review today. So I brought a RISC processor here. This is a Raspberry Pi. You can see compared to my hand, it's not that big. It's pretty small and it doesn't consume much electricity at all. It sits quietly. I have a little fan on here, but that's not needed. It just sits quietly just by plugging it in and it processes away. But now it has a really small CPU in there compared to like my computer, your desktop computer. It's very big. So this is not able to do nearly as many instructions per cycle as a big desktop computer. And we can talk about that, why that is that way. So if we come over here and we look at our Raspberry Pi processor that we got. So we have Raspberry Pi 3 here. So we have the ARM Cortex A53 processor. It has 512 kilobytes shared cache, and it processes at about 1.4 gigahertz. So if we go into that to read a little bit more about what the ARM Cortex is, well, first of all, it's an ARM processor, which means that it is a reduced instruction set. It's not a complex processor. And then we also see some cool words in here that we'll learn about today, such that it has a 2-wide decode superscalar processor. That sounds super cool. We don't know what that means yet, but we'll learn. And we see that it is more energy efficient alternative to the more powerful Cortex A57 microarchitecture. There's some other cool facts in here that has 64-byte cache lines. Like that's all cool words, but we'll learn about what these really mean today. Then we want to come over here and compare it to maybe some of the other competitors out there like Intel or AMD, which I'm sure you guys have heard of, and then compare it to ARM processors. We can see here that Intel is one of the most popular brands. They're in almost every computer in your office, to your home tablets, to your home computers, all over the place. These are normally pretty fast. Like we're talking 3 to 4 gigahertz now for modern day processors versus like 1 gigahertz for the ARM processors. And AMD has definitely been coming up there now recently. I mean, over the last couple years, they've been making some great CPUs for gaming or for just any other things. So if we look at the underlying instruction sets, yesterday we talked about what an instruction is, how it's exactly that. It's an instruction to the computer to process. If you look at the x86, so 32-bit processors that a lot of ARM computers use, we see that the set's not that terribly big comparatively. Like I know there's a lot here, but it's pretty small. And so these are kind of like words. They're simple instructions. So like move, where we copy data from one location to another. And we have other instructions like jump and add. Like these are, English words that we can understand. It adds two numbers together. That's awesome. If we can play around with this a little bit here, where we can actually program a processor in 32-bit for us to display hello world and then do a factorial. So, start running it. You see here that we're moving the value of hello world into this EAX thing, which is just a placeholder. It's just a bucket basically for data. And so we're moving hello world over there and storing it off in EAX, and we'll see that here on our next step, that we now have all of these values down here, which is hello world stored here in bytes. We push the value of 5 to EAX, step over a few more, and then we call this function factorial. And then we'll just let this run all the way through. See it printed hello world. And it's going to loop over a bunch of times. And then hopefully we should get 120 because we're asking for the factorial. And there we go. So that did a basic operation that we'd expect a computer to do pretty quickly. Print something to the screen for the user, hello world, and then also do some basic math, some arithmetic. So if we come over here and we look at Intel's 64-bit standard, they have a very massive PDF of all the different things that you can do in it and how to do it. And they look kind of similar, a lot of them, to how we had before. So this is add that we have here, and you can just say add and then two things. And there's some other ways of manipulating it, but for the most part, it's the same. They just added a lot more options. And then here's a little program where we print hello world, but in 64-bit using the Intel standard. So as you see here, we just have the hello world and a message here that we store into a variable. And then we just move it into where we want to display it and then call it. So the message just pushes it out to the standard out, which we'll learn about in a future lesson. And then we see it on our screen. Okay. So now that we went over all of discrete structures in our day one on the stream, and we covered a bit of computer internals, we are almost halfway done with all the boring stuff. We are so close to getting to the nitty-gritty programming, which you guys are all here for. But I want to talk about why are we learning these little nuanced things? Like, why do I care about the different types of processors? Why do I care about the instructions that are happening behind the scenes? I'm not planning on doing assembly programming or C programming. And that's a valid question. You're right. You don't have to learn these things. It's just like you don't have to learn the basics to golf. We can all go to a miniature putt-putt course and just hit the ball and get pretty successful. You can do that as a programmer as well. You can just say, I just want to learn Python. And we can go out there and we can teach you just Python. And you become a proficient Python programmer. But every time that you encounter a new challenge, where you have to go learn something, you just have to memorize it. You can't have building blocks of how the fundamentals work and build them up. Those fundamental building blocks allow really good programmers, like the professionals, the golfer that we look up to. They can look at the windage and do predictions and solve these complex problems of golfing because they're experts and they know the basics. That's what we're building you guys up to be, experts. We don't want you just to be a basic dev your entire life. So when it comes to learning a new skill, let's say you're learning a new networking library. If you fundamentally understand how networking and protocols work under the hood, you are able to quickly piece that knowledge together that you already have, and you build up that big puzzle of the new library that you're using. You just have to memorize the new words, but you don't have to learn any of the new technology behind the scenes. Whereas if you don't understand the building blocks, you just have to memorize what everything does. Memorize the name, memorize the input, memorize the output. That's not what we want programmers to be doing. We don't want you guys memorizing everything. It's not possible. There's too much in programming. There's too many languages, there's too many technologies, there's too many customers, there's too many libraries and packages coming out every single day. With programming languages like JavaScript, they have an amazing package manager called NPM, and Python has pip. That allows anybody in the world at any time to deploy a new library or a new package that you make up yourself. You can make up a new networking library, do networking in your completely own way, and if anybody downloads it, they have to learn your standard. But that means that there's millions of these coming out all the time, and there's a new better one every day that you have to learn. We want to make learning as seamless as possible and easy. Because if we have to continuously do it, we want to enjoy it, but we also want to be the best. I just want to show you guys that there is a reason here why we're doing this. And we're getting there. We're almost complete with this nitty-gritty. I know nobody loves learning about arithmetic or, you know, simple instructions and stuff like that. But there's a reason. Alright. So today we're going to be getting into how do CPUs prioritize work? How do they take a set of instructions and carry them out? How do we control those? And why are there different architectures? Why haven't we come to one conclusion by now? That, you know, one architecture is better than the other, or one methodology for doing something is better than the other. Okay, so let's start our book. We're going to bring it open in a new tab so we can come back here when we're ready. So today's book is called Squeezing Performance. Because the age-old problem is, how do we squeeze more and more power out of the same technology, out of the same CPUs, the same hardware? Because Intel wants to be able to sell you the next most powerful CPU every time. And this has been a question that's plagued engineers since the inception of modern day computing. So let's get into it today. In this section, we will cover techniques hardware engineers use in order to squeeze out as much performance from CPUs as possible. This is an interesting term that we haven't really covered before. So when we learned digital logic, we are learning the software and the digital side of things. That's what we control as software engineers. Hardware engineers are the guys that are making these motherboards and these PCBs. We should go look at what a PCB is. So if we start back here and we look at what just a PCB is, it's these ugly green boards that we've seen, you know, in your TV remotes, in your computers. Your motherboard may have a green hue or maybe some prettier color now. They make them in all colors. The color doesn't really matter too terribly much. But they have all these lanes on them, these little lines that are soldered on here. Well, I should say printed on. And these are little tiny electrical current paths that they can all follow. And all this stuff that we put on here, all these capacitors and resistors and all these banks and processors and all these different chips, all have a purpose on here. And optimizing the layout and the function and the consumption of energy and heat waste and all that is a hardware engineer's job. They sit down and they look at the requirements for what they need. They need a motherboard that can support this processor type, take this much power, supports HDMI, supports all these different technologies. They go out and they design it and they make it extremely optimized. And then they get it printed out where all these lines get put on it for electrical currents to flow through. And that field is still very much alive today. I know computers have been out for a while now, but they are still iterating over it. We're getting new motherboards every quarter, basically. But also now the technology has been evolving into space. Like we have SpaceX doing Starlink. They need to make their own custom motherboards and PCBs for all the technology that's going up into space. Well, that's a different requirement than the motherboard going in my computer here at my house. I don't have to worry about the vacuum of space or micrometeorites hitting it or being extremely energy efficient because I can just draw more power whenever I want and it just costs me extra. But on a small set, they really have to worry about that. So SpaceX engineers have to go out there and design their own custom motherboards, be able to do those needs that they need. Okay, so there's a common problem that has been plaguing hardware engineers for a while, and it's called the power wall. So for years, manufacturers pushed processors' thermodynamic limits by continuously increasing clock rates, which we'll get more into. But basically, a clock rate is how many times a processor can do an instruction per second. So clock rate of 60 would be 60 times a second. It can do 60 things in a second. That's your power. The more things you do in a second, the faster your CPU is. So they're always wanting to make that number bigger. And if every time you make that number bigger, eventually you start reaching theoretical maxes where you need the power of the sun to power the CPU. And so that's the problem here. Thermodynamics is a science of heat. The byproduct of power dissipates. Increasing the clock rate requires more power, which produces more heat, which is why we've gone from passive cooling designs, like our Raspberry Pi, which requires no cooling whatsoever, to these big water-cooled rigs now that we have. It's just to dissipate the heat now of these huge CPUs that are going in here, and they're just taking up a ton of power. So we have these big fans that go in here now, like these. All this liquid flowing in here, passing by these big fans. They have these big radiators that are 360 millimeters long to dissipate that heat, because that's the new problem. It's how much energy can I pass in here without lighting it a flame. Nobody wants their processor to catch fire and burn out their new amazing new computer when they're playing games. Okay, so there are many ways to dissipate heat. Heat sinks, fans, and liquid cooling are some examples that we just went over. However, with the ever-growing need for smaller computer systems, like smartphones, there is no room for fan to dissipate the heat. Therefore, alternative solutions to increase CPU performance, example pipelining in superscalar processors and multi-threading, were developed. As those solutions reached their peak speeds, multiprocessing solutions were also developed. So this is coming back to the point where, if we look at a phone, it doesn't have any fans. There's no big water cooling on this. And we wouldn't want that. If I had to have a big fan that I put in my pocket and it got extremely hot and burned my leg, nobody'd want to carry around a phone like that. So they can't do that. Engineers just can't do that. So those processors, while they do want to get more and more power out, right? They have to. Every new phone has to be the best. They have to also worry about those thermal loads, because they can't have the phone catching fire in your pocket, and they can't put a cooler on it. They have to just passively cool it, dissipate the heat into the case, and let it just air cool out. So those technologies that are developed to make CPUs do more things, but with less power, is where all of the growth has been in the last couple of years. By couple, I mean like last 20 years. So two of the solutions for these problems is called pipelining and instruction level parallelism, known as ILP. The pipelining and instruction level parallelism is a process of fitting as much data as possible into every single CPU cycle in order to get as much performance out of a CPU as possible. They are sometimes referred to by marketing terms like hyperthreading. So this is like if we had a bucket, and when you start putting stuff in your bucket, if you just didn't care how you were doing it, you're just throwing things in there in the first order they came, you wouldn't be able to fit the most in your bucket possible. But if you set everything next to your bucket and laid it all out, and strategically put everything into the bucket, so that way there was no air left in it, and then you carried your bucket, you'd be more efficient. That's what this is talking about. How can we fit the most instructions per CPU cycle in it, that we get the most efficiency out of each amount of energy that we're putting into it? Let's learn more about that. So we have our superscalar processors, that fancy word that we learned earlier, that ARM Cortex-A53 is bragging about, that they have a 2-wide decode superscalar processor, capable of dual issuing some instructions. So superscalar processors use a single fetch decode data path, leading to multiple execute stages, allowing for more than one instruction per clock cycle. So this is a really fancy way of saying they can do more than, or they can use a single fetch, which means that they go and they look for instructions. They're asking for something to do. They go and they get that instruction, they decode it into the language that they know, and they can do multiple things. So if that one instruction said to add a number, plus move something else, plus change the screen color to blue, it can do all three of those because they're not related to each other. So it could do multiple things at once, giving us more efficiency rather than just being able to do one thing. So the issue with this is the CPU must check for data dependencies at runtime. So if this first thing required an output for the second thing, and it tried to do them all in parallel, well, now you have a block. This one's just sitting there waiting. It can't do anything. It has to wait. And we don't want that because that's a waste. So it has to do a check here right before it does all that scheduling to make sure that there's no dependencies between them. Because if there is a dependency, you'll just load into the next one and move something else up. If the instruction does not need the result from an executing instruction, it is loaded into an empty execution stage. That's these. The compiler needs to move dependencies apart as much as possible to make this architecture effective. Additionally, it is important to realize that the fetch stage is broken into pipeline substages, allowing many instructions to be fetched at once. This is critical to enabling the CPU to check for data dependencies. Keep chugging along on this. We got one more page. So now we're learning about multi-threading and what multi-threaded processing is. Multi-threaded processing is the intelligent scheduling of instructions from two fetch decode data paths to a single execution stage. Each fetch decode path is called a thread and is implemented as hyper-threading in x86 CPUs. Whichever thread is ready to be executed first gets the execution stage. This intelligent scheduling improves execution stage utilization by preventing a stall while one process waits for an operand. So yeah, exactly that. So if things aren't dependent, we can execute them in parallel. There's no issues with that because they're just unique tasks, so we just run them all at once. But if they do have dependencies, it can hook back in here. These can run some logic beforehand and then just wait for it to get ready. That way we're saving this time of this process and doing it all at once here. So we have this parallelism coming into play. CPUs have been adding more and more threads and CPUs per processor. So at a simple scale of just 2 threads here, we can already see some of the optimization coming into play. Well, let's say you add 64 or 128 threads. Now you get a lot more efficiency than just one thread. And picture each thread as like a straw, where you can put an instruction in and you have to wait till it comes out the other end as the output. So having as many straws that you can push different instructions into just means more data throughput that you can do. And data throughput just means that it's the ability for you to compute things simultaneously. So then we can look up a quick guide, because we mentioned multi-threading and multi-processing. I don't know about you guys, but I'm curious to what the difference is. Here we go. Multi-threading and multi-processing in 10 minutes. That sounds good. It's about my attention span. So multi-threading and multi-processing are two ways to achieve multitasking. Think distributed computing in Python. So multitasking is useful in running functions and code in parallel, such as breaking down mathematical computations into multiple smaller parts, or splitting items in a for loop, which we'll learn about at a later time. And if they are independent of each other, as if they are independent of each other. Let's look at this really nice graphic here. Let's zoom in. So here we have like our old processors or a reduced instruction set processor. Tiny cluster problem. Yeah, exactly. So here we have a single-threaded, single-core processor, such as like a reduced instruction set computer or processor, where it just has one thread doing everything. So it shares all of the stacks, the data, the files, and their heap in the stack in the code for every single instruction that it wants to run. So you launch a program, it creates one of these, and it does everything one by one. Now, if we come over here to multiprocessing, where we take each core of the CPU and we basically just cut it off as if it's its own computer. So it's just multiple of these single process cores. It gets all of its own resources. So this is like Google Chrome and you open Notepad. They are completely separate. They don't share any code with running code between each other. And so if Notepad fails, Chrome stays open and vice versa. And if you type words in Notepad, they don't get typed in your Chrome instance. But if we move over here to our single process multi-threading, this is where we can share certain things. So if we have one program running like Chrome, and every time we open a new tab, we create a new thread for it. This means that we can share the same code, the same data, and the same files. You don't have to duplicate that into memory. That allows us to be even more efficient with our memory utilization. But you would create a new stack and a new heap for it. That way it can be sandboxed and they can do their own things while utilizing similar code in their own sandbox, so not controlling each other and not bumping into each other. If one screen's dark and the other screen's light, that doesn't matter because they're doing it in their own sandbox. So this is where a lot of our efficiency comes into play, when we can multi-thread and multi-process. And when we get to programming, we'll definitely start messing with some of these. So now let's look at another problem set that we have holding us back all the time. So our check on knowledge here is research and report on Moore's Law. We have to figure out who Moore is, what Moore's Law is, who created it. His name's probably Moore if we had to guess. What is it about, and is this law still true? What are today's biggest problems when trying to stick to Moore's Law? So, first step, let's take this name. Let's go Google it. Let's see what Google can do for us. There's a Wikipedia page for it. That's pretty nice. Let's go look at that. So Moore's Law is the observation that the number of transistors in a dense integrated circuit doubles about every 2 years. So Moore's Law is an observation and projection of a historical trend, rather than a law of physics. It is an empirical relationship linked to gains from experience in production. Let's take a look at this. So what does this mean? So if we look down here, we can see some super old processors that we really hopefully shouldn't be seeing in modern days. If we look up here, we can see some modern day beasts of CPUs, some really, really good ones. We can see that like every 2 years, it does kind of double. It kind of goes up in a straight line as time goes up, or as time goes on, the amount of transistors that they put on our electronics doubles. But what's a transistor? Let's go look that up. A transistor is a semiconductor device used to amplify or switch electronic signals and power. The transistor is one of the basic building blocks of modern electronics. Okay, so these are kind of like the switches that we were learning about the other day in digital logic that tied back all the way to discrete structures. So it seems like these are basically how we control the electronic signals. These are the physical gates that we discussed. It is composed of semiconductor material, usually with at least 3 terminals for conducting an electronic circuit. A voltage or current applied to one pair of the transistor's terminals controls the current through another pair of terminals. Because the controlled output power can be higher than the controlled input power, a transistor can amplify a signal. Okay, that's pretty cool. So it has 2 inputs and an output. Yeah. And so these things are kind of big. Like even though they're really, really tiny. They've gotten down to nanometer sizes now. Let's see, can we find the sizes here? Go back. Look up transistor sizes. Time. That sounds pretty cool. On PDF. So looks like they're getting about 22 nanometer tri-gate transistors, so 3 nodes on it, 2 inputs and an output. About 22 nanometers wide. That's crazy small. That's like hair follicles. How wide is hair? A piece of hair. In nanometers. Human hair is approximately 80,000 to 100,000 nanometers wide. That's crazy. So you can fit a bunch of transistors in a single follicle of hair. Just the width of a hair. So, keep looking through this page here. So it dates all the way back to 1947 was the first transistor. So they've been around over 80 years now. We're getting close to 80 years. Alright. Wow. Batteries produce over 5 billion transistors every second. Holy, that's a crap ton of transistors per year. It's equivalent to over 20 million transistors for every man, woman, and child on Earth. That's crazy. And we can see here that the quad-core Intel Core, the 3rd generation, they contain 1.48 billion transistors in that one CPU. That's crazy. That's a lot. Let's go back to this Moore's Law. So, we kind of understand what it is now. It's just this projection and observation that every 2 years it doubles the amount of transistors in a CPU. Okay, that's relatively simple. But I can definitely see how we're running into challenges. If every year we're doubling, you would have to double the size of a CPU every year, or get more efficient, or reduce the size by half between them. And I assume there's a lot of energy and heating problems then. That's probably where a lot of our heating problems come from. Let's see. Here we go. Maybe we can find out who made Moore's Law. We see that in 1959, this guy, Douglas Engelbart, studied the projected downscaling of integrated circuit size, publishing his results in the article Microelectronics and the Art of Similitude. Might be pronouncing that wrong, not an English major. Engelbart presented his findings at the 1960 International Solid State Circuits Conference. That sounds like a group of a lot of fun people. I'm sure that's where all the parties are. And this is where Moore was present in the audience. Okay, so it looks like Gordon Moore here was at this guy's first talk about how CPUs were just getting smaller and smaller in size. And then in 1965, Gordon Moore, who at the time was working as the Director of Research and Development at Fairchild Semiconductor, was asked to contribute to the 35th anniversary issue of Electronics magazine with a prediction of the future of the semiconductor components industry over the next 10 years. Zoom in on this text. It's kind of hard to read. Right here. All covering up. Beautiful. So, okay, so somebody asked him for this magazine, like, hey, where do you see this whole craze going? Like, do you see CPUs getting bigger? Do you see them doubling in size? Do you see them tripling in size? Do you see them staying the same? And so he probably went and looked. Let's see. Just over the next 10 years. His response was a brief article entitled Cramming More Components into Integrated Circuits. Within his editorial, he speculated that by 1975, it would be possible to contain as many as 65,000 components on a single quarter square inch semiconductor. I'm willing to bet, looking at that number, 1.6 billion transistors by now, he was probably wrong. Because what was it? He said by 1975 he thinks they'd be able to fit 65,000. Where are we at? We're like right here. 1975. It looks like he was a little zealous. It doesn't look like they were quite to that part now. It was per square inch, so maybe it's a slightly different metric. But okay, so now we know that it kind of came from a few different people. It kind of originally came from this guy, but then Moore kind of took it, and he was the voice of it. So that's probably why it got coined the Moore's Law. It makes sense. Moore posted a long linear relationship between device complexity, higher circuit density at reduced cost, and time. In 2015 interview, Moore noted of the 1965 article, I just did a wild expoliation, saying it's going to continue to double every year for the next 10 years. One historian on the law cites Stigler's law of economy to introduce the fact that the regular doubling of components was known to be many working in the field. Okay, so Moore, once again, was the first to observe it. He just kind of the biggest voice that said it for a magazine. So, kind of makes sense that we kind of coined it to him. Even though he didn't invent anything. He wasn't the first to come up with it. Let's see here. Okay. So in 1975, IEEE, which is this big... The IEEE is this big... Here, let's actually go into here. They're this basically governing body that we all abide by, because what they do is they push out a bunch of standards every year. That's what they do. They meet and they talk about different standards that should be there, such as how we should do Wi-Fi and define the standards for how devices should communicate over wireless signal. They also have other ones like programming standards where they define what programming compilers need and everything. So this is super awesome. They're definitely around today where they do a ton. They're coming out, I think they do it annually. They meet annually and they just, every year. So 1,200 conference proceedings every year. That's a ton. But yeah, so they just meet and they talk about, hey, what do we have to put into basically this law? Now, they don't enforce it, like you're not going to jail if you make your own standard. But if you're going to make a device and it needs to communicate with others, well, then you have to use their standards because everybody else is. That's what we agreed to. So they met in 1975 and Moore revised his forecast rate predicting semiconductor complexity will continue to double annually until about 1980s, after which it would decrease to a rate of doubling approximately every 2 years. Makes sense that it would slow down. He outlined several contributing factors for his exponential behavior. The advent of metal oxide semiconductors, so that must have been big at that time, the exponential rate of increase in die sizes, coupled with a decrease in defective densities. So that's another big thing. As technology has progressed, our engineering and also our big machines that are able to make these CPUs evolved, so they would have gotten better. Let's look up what a CPU. I forgot what it's called. The CPU die, D-I-E. Let's go look at these. So it's basically just the imprinting of a CPU. And we can see that these have just, we're able to make them bigger and more complex. Like you see that these are, I mean, there's a lot going on here. We have 6 cores on this one. Then they share a bunch of memory in the middle. Then they have all their ins and outs coming in here at the top. And they just have like a little memory buffer right here. So as they're able to make these bigger and bigger and bigger, we now have like AMD processors, which are massive. Like these things are huge compared to like other smaller processors. That picture. Look at that, the size of this person's hand. It basically takes up their whole hand, whereas this whole computer takes up my hand. This is just a processor and a desktop computer. By being able to make them bigger, they're just able to put more in it. Makes sense, but it definitely requires a lot more energy and a lot more cooling. So Moore's law is a violation of Murphy's law, where everything gets better and better. The observation was even seen as a self-fulfilling prophecy. If we look at Murphy's law, anything that can go wrong will go wrong. You'll hear about Murphy's law quite a lot, especially in software development. If you're working on a big project, every time you go to push, like to the prod, like you just made a brand new chat app and it's ready. You've tested it. You wrote a bunch of tests for it. You're confident it's ready for the public. Once you publish that, something's going to go wrong. If it can go wrong, it's going to go wrong. And that's Murphy's law. We just live by it. When it goes wrong, we fix it as quickly as possible. We try and plan for it, but it's going to happen. But alright. So far we're able to answer what it is, who created it, more. What is it about? We kind of explained that, where it's, basically about how technology is progressing over time. Now, is this law still true? Why or why not? Well, we can go back to this picture. We can see here that it kind of looks like it's starting to taper off in 2020. But, I mean, it's still looking pretty lively. Let's see. Is Moore's law dead? That's pretty strong verbiage. I'm going to take a look at this. Let's see what the verdict has to say about it. Accept your cookie. Moore's law states that the number of transistors per chip doubles every 2 years. Okay, good. So we're under the same understanding. So, since 1965, when Gordon Moore made this observation, it is held true. It is held true, and computer power has drastically increased while relative cost has decreased. But are we nearing the end of Moore's law? That's the question. That's what we want to know. Jump down a little bit. If Moore's law has died, computers will no longer see the same power improvements in the future. This means that many technological advances will rely purely on using more computers. This is neither efficient nor desirable for the world's climate. Computing already accounts for around 4% of all greenhouse gas emissions and 10% of the world's electricity usage. So I think this is interesting because we're kind of moving in that direction anyways already, with things like cryptocurrencies, which are decentralized currency exchanges. The whole point is being decentralized, so it's everybody in the world pooling their computers together to do complex tasks such as computing hashes. But we also see other like supercomputers. I mean, how do they get around it? They can't just have one giant processor. Well, no. Once again, they just start putting a whole bunch of computers called servers. They're just really efficient computers. They don't need to do things like display anything to us, so they get to be really efficient. in the fact that they could just make them really small, have a bunch of airflow coming out the back, and they just put a bunch of these together, all working together, and that's how they're doing it. Well, that's also kind of broken up. So I think this is kind of inevitable, where, if you want to train an AI, that's really computationally expensive. Like, the more complex an AI gets, the more we're going to have to rely on multiple computers. And I think our cost of processing time is going to keep going up, that we want more all the time. Same with like TikTok, like behind the scenes, they're using that algorithm to compute what to show you next. Well, the more variables that takes in, the more fine-tuned it gets, the more powerful those servers have to be to tell them what we want to see next. As more things like that keep growing, they're going to have to use multiple servers. So Moore's law is dead. Moore's law has been driven by the decreasing size of transistors. Many now argue that we are nearing the minimal transistor size. And the reason for that is this is due to a fundamental barrier presented by the size of atoms. That's how crazy small these things are getting, that we are now starting to bump into issues where the smallest units of measurement in our universe, atoms, the building blocks of everything, are our issue now in electricity. So IBM's current experimental transistors are only around 1 order of magnitude larger than the silicon atoms they are used to make them. So we're getting there. We're really close to the point where we cannot make them any smaller. So regardless of this problem, the growing costs of cooling, manufacturing transistors are also killing Moore's law. The more complex these chips get, the more it has to cost, right? $500 million for a 5 nanometer chip. Then there's Moore's second law, otherwise known as Rock's law, which states that the cost of a semiconductor chip fabrication plant doubles every year. Wow. There's also other technologies that are coming out, which kind of contradict Moore's law in a sense, because Moore's law is based on silicon processors. So if we look at a silicon-based processor, we can see that these are what we know. These are like the processors that we use, all these chips that are on our motherboards and stuff. These are the wafers that we use to make our processors. This is what we know today. This is what we use, this is how we know how to program and everything like that. Well, we have this new technology that's coming out called quantum computing. You can look at a quantum processor. That's pretty cool. I mean, these things are wicked. Like, they require sub-zero temperature, like, to really cool them down because they're doing things with quantum mechanics. They don't interact in a way that we know, where it's a 1 or 0, an on or an off. They have on, off, or both, and some other weird interactions between them. That's a whole nother subject, really complex. Many people spend their entire lives dedicated to it. But theoretically, a quantum computer can do everything a silicon-based computer can do almost instantaneously. So if this becomes true, it renders Moore's law obsolete. It doesn't matter if it's true or not, because we don't care if silicon-based processors double every year. Nobody would chase that anymore. So Moore's law would be dead because nobody would be making better silicon-based processors. They'd be making better quantum processors, if they can make it down to a scale that fits in home computers. Which we don't know if theoretically is possible, but we're definitely getting closer and closer. We now have working ones that you can actually interact with now. You can sign up and program them. But they still kind of look similar, like nice, pretty green. Okay, so we know what it's about. Is the law still true? We kind of explained that. While it is kind of true right now, but it is kind of dying. We know that it's dying. And it's probably going to die very, very soon. And so what are today's biggest problems when trying to stick to Moore's law? Well, it's kind of what we explained. Rising cost, even excluding our economy. If you're going to make these things smaller and bigger chips, it just costs more to manufacture them. Those manufacturing plants have to keep getting bigger and bigger and better technology. That it's just eventually going to get too expensive to keep progressing. It's no longer going to make sense for Intel to invest in the next CPU that has more transistors in it. We also have other rising technologies such as quantum computing or distributed computing. Why pay for a $1 million CPU that's slightly better than yours when you can just get a second computer and hook them together? All right, that concludes this check on knowledge. You guys have any questions? All right. Not looking like any questions are coming through. So we'll go back here. We'll do a little preview of what we're going to be looking at in the future, starting tomorrow. We're getting into multiprocessing because we learned about the issue and why we want multiprocessing and multi-threading. We haven't really learned about what they are and how they function under the hood. Like how does multiprocessing actually work and how do we do it as humans? Then after that, we're going to get into input and output. So this is how we input data, such as from your mouse, your keyboard, or if you have something coming from a network, such as the internet. They could be pulling like stock tickers. That'd be an input device. Then their output is like your monitors and stuff like that. We'll be getting into what those are. It's alright. If we have no questions, we'll take a look at some of these quiz questions. Oh, we have 1 minute. We have to do some matching terms. So using a single fetch diode data path leading to multiple execute stages. What is that? Does anybody know? Alright, if nobody knows that one, we'll move on to the next one. Maybe we can whittle it down. So intelligent scheduling of instructions from 2 fetch decodes. Okay, so there's 2 of them now. Data paths to a single execution stage. We need a little bit more time. We're gonna time out on this one. I think the first one, which is using a single fetch decode data path leading to multiple execute stages, is multi-threading. Okay. And then, oh man, we timed out already. Holy cow. We'll have to add more time on this one for previews. Okay, so we have implementation. So our second one was multi-threading, which means that this other one isn't multi-threading. That's a single stage. We can come back to our book quick, and we can look at what that single thing was called. Right here early on. We have our pipelining, which is the process of fitting as much data as possible in every CPU cycle in order to get as much performance out of it as possible. This is something that's called multi-threading. We have our superscalar processors, which use a single fetch decode data path leading to multiple execute stages. Okay, so it was superscalar for that first one. Yeah, you got it, decisions. Okay, let's reattempt this one. Or new preview. Switched them all up on us. We know this one is superscalar now, and we know the 2 or more is multi-threaded. So then we have this one, which is each stage of the FDE cycle simultaneously having an instruction. And we can choose between ILP or pipelining. Then the other one that we have is implementation techniques that allow overlapping execution of multiple instructions of a single fetch decode execute data path. Anybody have any ideas on this one? The first one and the second one is? I'm thinking because of the parallelism simultaneously, those are kind of synonyms. This one we'll choose pipelining. Let's see how we did. There we go. We got it our second time around. Like our theme song says, making failures is okay as long as we keep going forward. We can make whoopsies. Each stage of the FDE cycle simultaneously having its own instruction. That's called ILP or instruction level parallelism. Using a single fetch decode data path leading to multiple execute stages, allowing for more than one instruction per clock cycle. So that's that big piece there. More than one instruction per clock cycle, that's called that superscalar. Implementation technique that allows overlapping execution of multiple instructions in a single fetch decode. This here is the multiple overlapping, but in a single fetch. So we know that it starts out as a pipe, but then it does some cool math behind the scenes. Cool algorithms to figure out how to put it all together. Then we have our intelligent scheduling, which is what modern day computing does, of instructions from 2 fetch decode data paths to a single execution stage. That's multi-threading. All right. So with that, I'm going to do a quick review of who Rootkit is and how you guys can get some cool merch by doing our giveaway here on our website. We also have on our blog many other things that experts on our team or not on our team, any volunteer can do, such as like reversing encryption from an x86 assembly. That's pretty cool if you get into reverse engineering. We also have an article here talking about why competitive gaming could be an extreme danger in the future. With AIs becoming more possible on our modern day home computers, anybody can run an AI on their home computer. Therefore, anybody can cheat using machine learning and computer vision. We wrote an article about that and made our own. And then we have some other topics in here, such as binary protection using Go Embed and plugins, resolving variables in spell text from League of Legends. So this is a really cool tool made by Elijah, I believe, which just allows us to see all the different stats and League of Legends stuff, and it has some really cool details on networking, things like that you can check out if that interests you. We'll be continually growing this more and more and more. We have some older ones. Well, that's where we post our giveaways as well. So week 1's already concluded. Elijah announced his winners before going away, and we now have our week 2 giveaway up here as well. On our website, you can also see our certifications that we currently offer. This is continually growing as well. We have our level 2 certifications, which is our advanced computer science certificate, and our computer science certificate. So this is the basic one, this is the advanced one. This is comprised of multiple tier 1 certifications, and so we currently have these ones on our GitHub already, and the tests and everything built out for them. We have our Python certificate, Java, C, and Golang. And these are comprised of both a knowledge check, a personal check. So can you program, but can you also, know the basics of programming language, be able to implement them? And then also, can you describe to your colleagues and those around you, maybe you're looking for investors, something like that, can you describe what your program does? Can you leave comments explaining what the code does to others? Because just knowing Python isn't good enough to work on a team. You have to be able to communicate with your team. Explain what's going on, or else nobody's going to know, and nobody's going to take you seriously. We have our 100 Days of Rootkit section, which we've already seen. That's where we have everything else here on the side. We have our bustling Discord with 554 members on right now, where you can get support pretty much 24/7. There's some awesome people in here that volunteer to help others. No money received. They just do it because they enjoy doing it. I also want to mention one last time that our first 10K of our charity here is matched by an anonymous donor. So every dollar that you donate, Rootkit, a nonprofit, gets $2 that we're going to use to keep developing our certifications, but also help others that can't afford college to get these certifications and get jobs. And then last thing for the day is we'll check out our awesome merch store, which is continually rotating by the season. So right now we have these cool shirts in and these stickers that are online for right now. Once they're gone, though, they're gone. We're not reprinting these because we like to make it, a little bit exclusive. Those that are in early and are supporting us, they get a piece of history. They get to be here with our red panda and see our cool artwork on our shirts. These shirts are super nice. That's what I'm wearing right now. It feels great. It's a little bit stretchy. So there's that. I'll stick around for about 5 minutes, so if anybody has any questions, fire away. But we're going to end the stream here for the day. Take care, guys.